Welcome everyone to our session on improving science education. My name is Ralf Schumacher and I would like to introduce also Elsbeth Stern. Elsbeth Stern is one of my colleagues. She is the head of the department. She is professor for psychology and working on research and learning and cognition. And this is Lennart Schalk. He's also a cognitive scientist. He's a PhD and he's working in our projects. We intend to bring research on learning and instruction into the classroom. For this reason, we are collaborating with many teachers from high schools and from primary schools. And we have many teams that develop teaching materials. And we do carry out many experimental studies to evaluate the effectiveness of certain instructional settings. One of our main projects is a longitudinal study with 6,000 Swiss children we are carrying out for the next 15 years. And Elsbeth Stern will talk more about this. She will describe the details. The main intention of this project is to find out what are the long-term effects of improved and optimized science education and on cognition, on development of learning interests and things like that. In addition to this, we are constructing together with our teams in the MINT Learning Center. MINT stands for Mathematics, Informatics, Natural Science and Technology. We are constructing teaching units for high school teachers on mainly mathematical, physical and chemical topics. And there we try to apply results from research on learning and instruction into concrete mathematical and other scientific topics, together with teachers which we hire from their schools. So we have really a large and interdisciplinary group. And what I'm now doing is, in the first part, I'm going to present an overview of the teaching materials and of the way in which we tend to make science education more effective. Let's start with some tasks for you to activate you cognitively, because the general title is how can we improve science education by cognitively activating forms of learning? This term of cognitively activating forms of learning just means that those are forms of learning that stimulate knowledge construction, that gives the students a real motive to change their conceptual framework. What do we mean by intelligent knowledge? I would like to give you a task. The task is you now are asked to test the following rule. The rule is, if there is a vowel on the one side of the card, there must be an even number on its other side. These are the cards, 4 cards with an A and B, and 4 and a 3. And I now would like to ask you, which of those cards have to be turned in order to check whether this rule is fulfilled or not. Who would like to make a hypothesis? Thank you. Mark? What? Okay. Yeah, why not? Okay. Talk to your neighbor and think about the I don't need this now, thank you. Okay, who wants to make a suggestion? Which card has to be turned? Don't be shy. What do you think, for instance? Yes, on the other side of the card is either a number or a vowel.
Well,
or
I would guess maybe B.
B?
Yeah. But
what kind? The logic is a conditional. If there is a vowel on one side, then there has to be an even number on the other side.
Oh,
that's the rule, an even number. You wanted to say?
Según la secuencia. La tarjeta 3, un número escogería.
Number 3, okay. Are there other options and expectations? For instance, Laura, what would you say? Uh-huh. That's interesting.
Oh, sorry. A and 4?
A and 4. A is correct because if on the other side of that card there were an uneven number, then this rule would be falsified.
I will only turn A because I already know 3 is an even number, 4 is an odd number, B is not it's not a vowel, A is a vowel, so I have to check if in the other side it's an even number.
Mm-hmm. Correct, yes, very good. I guess the idea behind the suggestion that you have to turn 4 is that you say if on the other side of this card with the even number there is a vowel, then it's correct, otherwise it's incorrect. But the rule was not if there is an even number on the one side, there has to be a vowel, but the rule was if there is a vowel, then there has to be an even number. Therefore, 4 is not correct. And as you suggested, 3, of course, is correct because otherwise the rule would be falsified. And if you present this kind of problem to an audience like this, typically 10% of the persons get the right solutions and 90% make some kind of mistake. But interestingly, if you present a problem that has the same isomorphic structure, like this one, for instance, here you have persons in a disco and they are drinking several drinks, and the rule now that has to be tested is if you order beer, you have to be at least 16 years old. And now the question is, which person has to be checked by the police? What do you think? Does the police have to check Peter? Yes, they have to check Peter because he's drinking beer. They have to check whether he's at least 16 years old. Then they have to check Klaus because he's just 15, and they have to find out what kind of beverage he's drinking. If you present this problem to the same audience, then you see 100% of the same persons get the correct answer. And this is an interesting finding because it shows that if a certain problem is presented to you in a rather familiar context, then your rate of solution is much, much higher as if it's this same problem is presented to you in a rather abstract context. And this is found very often, that it shows that there is no spontaneous transfer between problems with isomorphic structure. This indicates that human cognition is rather domain specific, that you can solve certain problems within the area within you learn something in which you are familiar with things, but it makes difficulties for you to transfer this to other areas. And the problem of knowledge transfer is always that one has difficulties of recognizing the common elements, the common knowledge elements that are in both tasks present, in the target task and in the learning task. And this is exactly what we mean by intelligent knowledge. Intelligent knowledge is that kind of knowledge that is structured in that way that it really enables and facilitates transfer. And that's the kind of structure and knowledge that we are working on. So in order to develop intelligent knowledge, one has to restructure one's conceptual knowledge. Usually children start with rather classifying objects in the world by superficial criteria. They focus on surface features. And for instance, they classify animals according to the area, the environment in which they live. But of course, we have to bring them to classifications that are directed by more abstract criteria. And then they find out that they have much more in common than in the other classification. So what I just wanted to show by this well-known Ways and selection task is that we are interested in establishing intelligent knowledge that really facilitates knowledge transfer, so that, for instance, students who were in our physics lessons are able to acknowledge that these three cases, which look superficially different, this reservoir, the crossbow, and the bowl that is moving there, that they have something in common. Do you have suggestions what they could have in common? Any ideas? They look different. The reservoirs full of water. the crossbow is some kind of weapon, and this other physical device is just rolling there. What they have in common is that in all cases, there is mechanical energy stored. You have mechanical energy in this reservoir because of its height. You have mechanical energy that's stored in this crossbow because it's pulled back. And as long as this bowl is moving, you have mechanical energy because it's moving in this direction, and it will only release this energy when it hits this barrier. This kind of knowledge that we are interested in, and in the teaching units that we are developing with our teachers in our MINT Learning Center, we are very much eager to implement the latest results of research on learning and instruction to facilitate this kind of knowledge. And I'll now give you a rough overview of what we are doing. The first thing, that's quite similar to what just recently Ken Ködinger presented, namely that what the teacher needs is really a very specialized and precise knowledge of the students' prior knowledge in order to connect to this knowledge. And of course, that the teacher has to know what kind of difficulties the students might have, what kind of interesting misconceptions they might have, and which interesting misconceptions might give rise to interesting difficulties of understanding. And for this reason, all our teaching units come together with a pre-test and a post-test that is adapted specifically to the specific topic. This is an example from a teaching unit on mechanics. We use this as a starting question for the students. For instance, what? Yes. So you have two persons standing on a skateboard. They both have the same weight. The skateboards are quite similar. Both are connected by a rope. One of the persons is actually actively pulling the rope. The other person just passively holds it. And now the question is, what happens if they are doing that? The first option is the person on the left stays at her position, whereas the person on the right moves towards the person on the left, because the person on the left is active. Who would say this is the correct answer? Lift your hands, please. Okay, nobody wants that. Second option is both persons move and they meet in the middle. Who would say that this is the correct answer? And the third option, both persons move, but they meet at a point that is closer to the left person. Who would say that this is correct? Just one. Actually, it was the second option, because there is Newton's third axiom, according to which for each force there is a force of the same amount but of the contrary direction. So it doesn't make a difference whether you're just passively holding the rope or whether you're actively pulling. And by asking this kind of questions, of course, before teaching mechanics, we already get some information. What are the students' conceptions? What are their possible misconceptions? And for instance, this is another example also from physics education, focusing on thermodynamics. Here in this case, we have a glass of water under a vacuum bell jar. The air is evacuated from this, and finally the water will start to boil. And now the question is, which of the following claims is true? At the normal room temperature, due to the boiling, the water is getting hotter, but it does not reach 100 degrees Celsius. Due to the boiling, the water is getting colder. Due to the boiling, the water is getting hotter until it reaches the temperature of 100 degrees Celsius. Once it has reached the temperature does not rise any longer. Or the fourth option, the temperature of the water remains constant. Who would say that the first option is attractive? It's all at room temperature. There's no heat under the water. Anyhow, it boils. Who would say that the second option is attractive? It's getting colder. Or the third option, that it reaches 100 degrees Celsius. Or the fourth option, okay, actually it is the second option, because in this process of boiling at room temperature, the water needs energy to transform from the state of a liquid into that of a gas. Since there is no heat added, it has to get the energy from the water, and for this reason, the temperature of the water goes down. This is a typical pre-test question of our tests for thermodynamics. This is another one that's easy, I think, for you. Now we have an ice block that has a temperature of -8 degrees Celsius. This ice block is slowly and constantly heated, and the temperature is measured as a function of time. Now the question is, which of the following diagrams describes this process correctly? Is it rising constantly, as in the first one? Is it rising in the way that it reaches a certain limit, as in the second diagram? Or is it the third diagram, which looks like some kind of geometrical shape? What are the beliefs of you? Who is for the first one? And for the second? For the third? Oh, Kevin and Elspeth, yes. And you already all know that whenever Elspeth is raising her hand, you have to do that too. Okay, yes. Exactly, this is the right answer, but interestingly, we found out that students' answers are just by chance. Even the 16-year-olds at the Swiss gymnasiums, I have no knowledge about that. This is an example of a pre-test for mathematics, for calculus. Designing a pre-test is often much more demanding than designing a post-test. If you're designing a post-test, you just can build questions concerning the contents that were taught. But if you're thinking about designing a pre-test, you always face the difficulty that you really have to think through what are the kinds of misconceptions that they can bring to school and what kind of prior knowledge is really needed for these lessons. And in this scenario, we are considering an infinitely long ball path in which a bowl lies that can be pushed. Yes, it's fine, thanks. The bowl can be pushed forwards and backwards, and due to friction, this bowl comes to a stop after a certain time of moving. And we have certain questions designed around the scenario. Anna, for instance, pushes the bowl again and again. After the first push, it rolls 10 meters. Since Anna is getting tired, after each push, the bowl rolls only half of the distance of the preceding push. And which of the following claims is true? First option, the bowl will reach any high position. After n pushes, the bowl stops at position n multiplied by 0.5. And third, the bowl will never pass position 20. Now you disconnected it. Okay. And the fourth option is the bowl will reach position 20 after a finite number of pushes. Who has any intuitions about that? Elspeth? Okay. It's the third one. The bowl will never pass position 20. So, and with this kind of information, of course, the teacher has a very good preparation for designing his lessons. And in particular, if he has now found out what are typical misconceptions that might cause difficulties in understanding, he can later on actively pick up these difficulties and focus on them. And I will show in a moment how we suggest that this could be done. The second step that has to do with preparation, science lessons, is that as an entry into the lessons, we always try to offer some kind of problem that is designed in that way, that is interesting for the students, but on the other hand, that they will not be able either to predict or to explain the phenomena that will take place. So they have some interesting phenomenon that clearly shows them the limits of their knowledge and makes them ask, well, what is the reason behind this? How can I predict and explain this? For instance, in a lesson about thermodynamics, we started with this experiment. We had a balloon. We put it above a candle, and surprisingly, it did not explode. Nothing happened. Children were surprised. They started asking. After a while, they found out that there was water in the balloon. And then the next question was, which property of the water was it that explains that the balloon does not explode? And of course, this was the step when we started to introduce the concept of heat capacity, that there are different heat capacities for different materials, and that you can rely on this concept of heat capacity to explain phenomena like this not bursting balloon. Another example from our lessons on mechanics. This I photographed in a museum near Zurich. You see there are 3 different bath balls, and the 3 bowls are lying at the same height. They can be released at the same time. And so now the crucial question is whether all these 3 bowls will reach the goal at the same time, or whether they will really arrive at the goal at different times. What are your intuitions? Will the ball on the shortest path will be the fastest one, or will the bowl on the longest path will be that the bowl that takes most long? You would say that the short one will take the longest time?
I don't remember the name, but it's the special curve. It's the fastest path.
Mm-hmm. So your prediction would be that they don't arrive at the same time? At the same time? Not. Mm-hmm. And which will come first? Okay, good. And the second bowl?
The second, I think the first path, and the last one, the second path.
Ah, yeah.
I think.
We use this phenomenon in order to introduce the mechanical concepts of kinetic energy and potential energy. And we tell the students first, when we explain it to them, that at the beginning, the 3 bowls have the same potential energy. And during the movement, they turn this potential energy into kinetic energy. But now the decisive point is when the potential energy is turned into the kinetic energy. And you were exactly right. This bowl has this long way to accelerate. So 2/3 of the whole parts, it's traveling with a rather high speed. In contrast, this one constantly accelerates, but 90% of the time it's traveling with a speed that is significantly slower than that of the bowl on the longer path. And this bowl in the middle has also the advantage that it also reaches its high speed at a very early point. And for this reason, this bowl is the last one, this is the second one, and this is the first one. And by the friction is very small, so we can abstract from it in this case. Yes, it's good. It's metal. Our experience with introducing and the lessons in this way is that students pay much more attention, are much more interested, and that they are much more fully aware of the limits of their own knowledge, so they are much more open for the theories and concepts offered by the science to explain what happened. I think I have another one. I skip that. We presented this to people working at nuclear power plants, and of course they are selling electricity, but they were not able to answer these questions of how changing current, alternating current, is able to travel from point A to B. But just one final example. This is also from thermodynamics, and I would like to ask you to think about this problem. If you regard 2 amounts of water, it's the same amount, but it has different temperature. In the one case, the temperature is 20 degrees Celsius, and in the other case, it's 50 degrees Celsius. If you mix these same amounts of water, what kind of temperature will you get? What do you suggest? Yes, about middle, that means how much is it? Exactly, you're right, it's 35. The difference was 30, and it's really the middle. Now, the next point is, if you regard, again, the same amount of material, on the one hand you have water of 30 degrees Celsius, on the other hand you have ice of 0 degrees Celsius, and if you mix them, what temperature will you get? Would you again say you get the middle? Oh, good. That's maybe because I asked in this way. Yes. Actually, you will get some temperature that lies around about a little bit above 0 degrees. And this is a way, of course, to introduce this concept to students. So now they start thinking, why can that be? And it's really conflicting with their expectations. And the reason behind this is that in this case, the ice has to be melted. So it has to go from the state of being a solid block of ice to the state of being a liquid. And this, of course, absorbs energy. And for this reason, the rise of the temperature is not proportional as it was in the other case. I've already mentioned these points, that learners recognize much better the limits of their own knowledge, that they usually show greater interests in the phenomena, and that they are much more open for the concepts and theories offered by the scientific explanations. We are still on the point of thinking about how can we prepare students better for learning. And there are many ideas about this. For instance, if you are intending to teach the conservation of energy and momentum to students by using Newton's cradle, you can think about how can I really better prepare them so that they are much more open for this kind of topic. There are many suggestions to do that. We don't have any data about this example. Maybe it worked, I don't know. But there are other interesting data about a different procedure, about a different learning setting. And this is really some kind of instructional setting that we intend to apply quite frequently in different domains, in different content area. And this experimental study published by Schwartz and his colleagues in 2011, they focused on the question, is it always the best way to proceed by presenting a theory and concepts at first and then instructing the students to practice certain tasks in order to consolidate this knowledge? Or are there other ways that prepare them better for the learning and prepare them better for the concepts and theories offered by science? In this case, they carried out the study, and I'm fully aware of the devices here now, and I don't hit them any longer. The participants in the study were around about 250 students. Their age was between 15 and 16, and they were comparing two different kinds of instructional settings. On the one hand, they had regular lessons where they introduced a concept, in this case, the concept of density, which is described as the ratio of matter per volume in the normal way by talent practice. And on the other hand, they thought it might be better before presenting the theory and the contents to them that they get some kind of preliminary tasks that really make them think through the deep structure. And the problem presented to them was the following. It had the following cover story. Here are 3 companies that are carrying clowns to birthday parties, and these clowns are in buses. And the more crowded the buses are, the more grumpier the clowns arrived at the birthday parties. So the task for the students now was, as a preparation, to invent an index for crowdedness in order to develop one kind of measure that would give you some information about the qualities of this clown delivering bus companies. And you can easily see that the measure they had to invent was quite similar to the concept of density, namely mass per unit of volume. And the fact that they were working on this problem and then afterwards received the information about what density is, actually prepared them better because they were deeply thinking through the underlying structure, and they were performing better in later transfer tasks than the other students who got the same information and who were working on this same clown problem after they got the information just to practice what they had learned. And this is a very interesting result because it shows that although you have the same amount of time, just by changing the order in which you are presenting contents, you can make a difference in learning achievements. And since this is so attractive, we tried to implement this in our teaching units in many different cases. Lennart Schalk will focus on one of these implementations soon. We are now using this for students to instruct them to invent an index that describes the slope of linear graphs. They are presented with a number of linear graphs of different slope, and the scenario is the following, that we have Alice who is at the telephone, she's calling her friend Bob, and she has to invent an index that makes it possible to communicate the slope of these linear graphs so that Bob will understand that. And in the control condition, then the order is reversed. We first present them the theory, what slope is, how you calculate it, and then we use the very same tasks for them to practice in order to consolidate their knowledge. And we found out that this makes a difference on the learning outcome, that the students who first had to invent something and who had deeply think through the problem, that they had better learning gains than the others. In the second case, we developed some instructions for them to discover by themselves the difference between temperature and internal energy. It goes like this. Just consider this large bowl that contains some water, and the water is filled into two bowls, but there were different amounts of water filled in these two bowls, and now the task for the students is compare those different amounts of water in the two bowls, and what do they have in common, and what is different between them. And by guiding them by this instruction, of course, we expect that they would say, well, they have the same temperature because they are from the same bowl, but on the other hand, different amounts of heat energy or of thermic energy are in them, so that's what difference between them. And the second task is that they have to consider now the following case. You have again two bowls filled with the same amount of material, but on the one hand you have cold water, on the other hand you have hot water. Then you pour the cold water into the hot water or reverse, and now you have again to consider what changed and what stayed the same. In this case, the temperature changed and the amount of thermic energy was the same. And we have a couple of instructions which are quite similar to that, and as a result, we would like them to discover, in their own words, a conceptual distinction that corresponds to the distinction between temperature and internal energy, something like that. This is another way of preparing them for learning, of preparing them for that theories and concepts that are offered by scientific theories. I have a third example, but I'm unsure whether I have enough time to present that. It's okay, then I can come back to that maybe in the discussion. It's some instruction in which they are guided by very specific tasks to discover the difference between the three mechanical kinds of energy: kinetic energy, strain energy, and potential energy of the height. Okay, so these second and third points, they were mainly about how to prepare learners for learning. How can we activate them before we present the stuff to them? And now this point number 4, the self-explanation, that is about the point, how can we really deepen and consolidate their knowledge, what they have learned. There's a large literature on so-called self-explanations. Self-explanations are explanations that person give for themselves in order to deepen their knowledge. And the self does not mean that they can invent something, but the self means that you are yourself the person who is addressed by this explanation. And usually these self-explanations are used on the one hand within the lessons to ask them, have you really understood something? You can also use it to pick up certain interesting misconceptions if you, for instance, identified that they are not able to give the right answer about the skateboard question, that they think that the person who is passive moves towards the person who is actively pulling, then you can use for a task for prompting a self-explanation by asking them, how would you explain to somebody who has this misconception why he is wrong and why both persons are moving? So the idea behind these self-explanation prompts is really to prompt focused processing, that they do not focus on superficial properties, but that they are really guided by these instructions to think through the relevant points. And in Germany, Berthold and Renkel are quite famous for their work on mathematical learning and algebra and probability learning. And they often use self-explanation prompts to consolidate and to deepen understanding of these calculation procedures. In this case, they have the story of a mountain bike tour. You are participating in a mountain bike tour and you're there for 2 days, and each day you get helmets of different color, and they had to calculate the probability of what is the probability that you would get both a green and a red helmet. And of course there were also 2 conditions. One condition was the self-explanation condition, where students had to explain, for instance, why do you calculate the probability by multiplying the number of helmets with the number of days. And the other condition was in the control group that they were guided to read the text very carefully, and for instance to mark by these 3 colors that you see there the corresponding parts of the text that are belonging together. So this was also some kind of instruction that really instructed them to read the text carefully and identify the corresponding text parts. And in this study, although both conditions were quite cognitively activating, the self-explanation group showed better performance and better learning gains than the other group. And therefore, we very often use these self-explanation prompts to improve the focused processing of the relevant contents, and to guide them also to reflect about their own understanding so that they are able to identify what they really understood, and they discover maybe misunderstandings that they would not have discovered otherwise. And of course, you can also use it in mathematical lessons, because you can actively describe which problem-solving strategies are correct, and also you can represent those strategies that are incorrect actively as incorrect learning strategies. One example from our mechanics lessons is the following. It's about a cube that is falling down. Now you're confronted with a person who says, well, someone believes that in this particular case there is no reactive force to the gravitational force, and how would you explain to this person why her view is incorrect? So this is just to make sure that students did not just learn to repeat Newton's third axiom, that for each force there is some kind of reactive force that has the same amount but the contrary direction, but that they are really acquired that kind of intelligent and flexible knowledge that they are able to apply it to different situations. And in this case, we would expect something that they say, well, it's not only that the Earth attracts the cube, but also the cube attracts the Earth, and the forces of both are the same. But since there is this big difference in matter, the Earth has much more than this cube, it's not the Earth that moves in the direction of the cube, but the cube moves in the direction of the Earth. And it's really interesting. Many teachers often make the objection that they say, well, if you talk about misconceptions with them, will this not have the effect of inducing misconceptions by this kind of instructions? But it turned out that, and this is a general evidence for which there are many empirical studies, that talking about misconceptions as misconceptions and focusing on them really has the better learning effect than just telling them what is true and correct. Okay, since we don't have much time, I skip this. Another way of confronting misconceptions is the so-called holistic mental model confrontation. Some of the authors who were developing this literature on self-explanations, Micheline Chi, for instance, they asked themselves the questions, is prompting self-explanations always the best way of effectively teaching abstract contents, or are there situations in which it might be better flexibly to apply other kinds of instructional settings? And for this reason, to find this out, they compared two instructional settings. On the one hand, self-explanation prompts, on the other hand, something else. It was published in this paper from 2012, The Effectiveness of Holistic Mental Model Confrontation in Driving Conceptual Change. In this case, they had 84 participants. They were medical students. I can give it to you later. Okay. They were in their early 20s, and in the experimental group, they got this instruction to confront certain mental models holistically. I will focus on that in a minute. And the other group had self-explanation prompts. And this holistic mental model confrontation was presented to them in this way. They were informed, in this case it was about biology, about the human blood circuit, and the model on the left, that's the novice model containing interesting everyday conceptions about the human blood circuit and many false things. On the right hand you have the expert model, and the students were of course told on the left hand there is the novice model, on the right hand you have the correct expert model, and your task now is, guided by very specific questions, please describe all relevant differences between these two models. And the other group, they were guided by self-explanation prompts, so both groups spent the same amount of time, both groups got very cognitively activating instructions, so they had both a real chance to improve their learning. But interestingly, it turned out that the group that was working with this holistic mental model confrontation showed much better learning gains. In particular, 90% of the students who worked with this mental model confrontation after that understood more about the relevant facts about the human blood circuit, but only 64% of the students who were working with the self-explanations. Okay, Leonard just gave me the sign that I still have 5 minutes. I think I just close by showing how we are implementing this mental model confrontation in our teaching units. One area in which there are many misconceptions and wrong ideas about scientific facts is the area about functioning of batteries. We have one teaching unit in chemistry on how batteries work. And often students have ideas about the electrons, why they flow, that are very wild and not very adequate. And here we have the lay of the novice model. For instance, this point, when the electrons have reached the light bulb, they release their energy so that the light bulb grows. Or they think that, for instance, the zinc that's in here wants to get rid of its electrons and wants to give these electrons away. And since it does so, there is some kind of pressure of electrons within the battery. And whenever you close the circuit, thank you. Seems to be some kind of running gag that I'm stumbling over that. And whenever you close the circuit, like opening a faucet, then the electrons start to flow. So there are many misconceptions about the flow of electrons within batteries that are mainly due to this water analogy, why they flow. And then we ask them to confront this novice model of the function of a battery with the expert model of a battery that states, of course, both materials, the manganese dioxide and the zinc, they both are attracting the electrons. However, the way in which the zinc attracts the electrons is weaker than the manganese dioxide. For this reason, this manganese dioxide gets electrons from the zinc, and it's not that the zinc wants to dispense this. And this is what we are currently examining in an empirical study with several students, and we are still waiting for the results, how effective this was. These are the questions that are guiding the students. I think I have to emphasize that all our instructions are not just open questions, but that we really guide the students by very specific instructions to make sure that at every step of their learning they have all relevant help they need to do this, and that they're also guided by these questions exactly to find out the points that we are interested in. And this is a much better way of communicating them how batteries work than just by giving them the truth and telling them how they work. You can use this kind of instructional setting in many areas. It's not just restricted to the human blood circuit or batteries. You can use it, for instance, also in mathematics. You can, for instance, confront different ways of solving an equations by a novice, for instance, by the solving of equations by an expert. So there is many room for applying this very effective way of teaching demanding contents. If I still have, Leonard, 1 minute, I just close by focusing on so-called metacognitive questions. Metacognition, as you know, is cognition about one's own cognition. We use, as I already said, these pre- and post-tests to examine what students know. This gives the teacher more information. But of course, it's also possible to train the students to get this information about their own state of learning by themselves. And for this reason, in all our teaching units, we regularly implement tasks where they have to ask themselves with very specific questions, did I really understand this particular topic or not? And of course, the key to success is always in this context that you cannot just generally ask these questions, did you understand everything or have you problems about understanding, but you have to really ask to the point, did you understand where the reactive force is in the case of the cube falling down, or did you understand why the view is wrong, that the zinc wants to release its electrons and that there is some kind of pressure of the electrons that gives rise to the flow of them in the battery. There is a lot of empirical evidence for this kind of teaching. I'm not going into the details. Maybe we can do this in the discussion afterwards, but I just want to mention that there is abundant evidence comparing asking metacognitive questions with other also cognitively activating and serious instructions spending the same amount of time on this topic. Okay, this is what I wanted to present. This is how we in the Swiss MINT Learning Center try to implement research from learning on instruction in order to create intelligent knowledge in the context of the natural sciences. Thank you for your attention. And Karen, do we have now time for discussion?
Voy a tratar de hacer esto en español y si no puedo, voy a hablar en inglés. ¿Está bien? I'm going to try this out in Spanish for a little bit because I see most of you are wearing headphones. And then if I get stuck, I'll switch to English. El profesor Schumacher ha enseñado diferentes maneras de enseñanza para las ciencias. Nosotros como educadores tenemos aquí, voy en inglés, we are charged with the mission to pay attention to what they're talking about and the models that they are coming up with and seeing what has relevance for our context. So, in thinking about what Dr. Schumacher has just presented, and thinking about how we approach education, science education in our schools, what for you has stuck out as something interesting that you might want to try in your classrooms? Is it, he outlined some steps, and getting them to access their prior knowledge and getting them to identify their misconceptions. He talked about some steps like that. He talked about pre-tests to surface misconceptions in students. He also talked about self-evaluations, or self-explanations, and he discussed holistic comparisons of models. So find a group that you can talk to side by side with each other and pull out some ideas that you think would hold relevance for your context. We have an important assignment here because we have a way to look at the models that they're showing and then ask the experts to kind of give us some guidance. So this is a great opportunity. So if you can turn to your neighbors, kind of think of some ideas that you want to maybe pull out, and then we can turn it back to Dr. Schumacher if you have any questions. Sound good? ¿Está bien? Okay. Ahora es tiempo para discusión. Yes.
De ciencia. Y ese problema de ciencia, cualquier cosa que vamos a enseñar, debe ser ¿cómo decir? Previamente preparado por el maestro, pero no dado la respuesta por el maestro, sino dado la respuesta por los mismos alumnos para que ellos encuentren dentro de sus errores lo que realmente él entendió. Y a lo mejor es que no entendió realmente el problema que el profesor le está poniendo. Eso es lo que yo entendí. Y es por eso que debemos siempre tratar de que no el maestro dé la respuesta, sino que los alumnos emitan sus conceptos y sus conocimientos de acuerdo al ejemplo que estamos dando. Y finalmente llegaremos al conocimiento verdadero cuando ya algún alumno o alguien o la mayoría en un porcentaje de alumnos llegaron a una respuesta acertada. Eso es lo que yo encontré. Gracias.
What she understands from your presentation is the importance of having the students surface their misconceptions instead of the teacher or the instructor giving the correct answer. Is that?
Thank you very much for your question. This process of examining the misconceptions they might have before the lessons or after the lessons, and also this process of self-detecting misunderstandings or failures of understanding. This is not replacing good instructions about the truth. It's part of that. So it always makes sense, for instance, to start with some kind of cognitively activating problem. They are intended to work through, think deeply about the structure. Then the teacher offers to them, of course, the correct theory. Maybe then even that they practice something about that. But then it seems to be that research has shown that if you actively address misconceptions and focus on them and let them really explain why a certain idea is false, then thereby you really activate their knowledge that this is wrong and put it on a higher level of activation, so that, for instance, when they are reflecting on whether a certain problem-solving strategy is incorrect, and when they are in an examination situation, when they usually tend to apply the wrong strategy, if they before had reflected on that, and this knowledge of why this strategy is incorrect, then the probability that they might rely on that strategy is much higher. So considering misconceptions and talking about them is an important part, but on the other hand, of course, telling them the true theory and practicing still remains an important part too. Is this correct?
Hello, Doctor. Not all misconceptions are misconceptions. There are certain situations students just use the wrong words for the explanation. How would you deal with the situation? There is a lot of research that explains about not all misconceptions are misconceptions. There are cognitive functions that sometimes students use to mislink these actual words. How do we deal with that? And that's the first question.
That's an interesting question because it's exactly what we are using when, for instance, we are applying this technique of inventing with contrasting cases. For instance, if you want in thermodynamics, let's say, invent some distinction that corresponds to the distinction between temperature and internal energy, you do not at first expect that they will be using the correct scientific terms. They will say the warmth or the heat or whatever, something like that. So they will describe, for instance, internal energy in their own words. And the idea about this is that they first have to start to think about why do we might need this kind of distinction in physics in order to account for certain phenomena and differences. And then, of course, after they suggested their own concepts and words in order to describe this distinction, then the teacher has to take up their suggestions and to continue and say, well, what you described as difference between temperature and heat, that's called in physics the difference between temperature or something else. Or for instance, in case of these questions when they had to develop a measure, an index for the slope of linear graphs, many of the students productively failed. They suggested something wrong. For instance, some of them just described the indices for 2 points on this line. And of course, this is not a suitable solution of that. But then, of course, you can, after they suggested that, take it up in class and discuss what is correct about their suggestion and what has to be reformulated. And for instance, you can use for also these self-explanation prompts as a good example. For instance, when you confront something with the task that you say, well, think about that person. He or she was not present at the lesson when we were introducing Newton's third axiom or something like that. And this novice describes a certain fact in his own words in that way. How would you, this would then be part of the task, explain to that person what of her view is correct and what of her view is incorrect? And then this also again prompts focus processing of what is really to the point and what is just some kind of surface feature. Is this satisfying? Good. Good. I tried.
What are your thoughts on a preconception? That where they're at is a preconception as opposed to a misconception?
So it's a good point, yes. Preconception, I would say, is some kind of prior knowledge that can be extended and used in order to introduce some kind of concept. But a misconception would be something that is plainly incompatible with the scientific view.
Sure. I feel that sometimes students, when they are just working in physics, they miss a lot of things, and it's not very interesting. If you put physics in a context with biology and chemistry, in a situation, for instance, to visit a holiday in the park or things like that, and then you could introduce a kind of integrated knowledge, putting physics, chemistry, and biology together. This would be more interesting for the students. And I think he would go further than in this, just this way. I do understand you are talking about prior knowledge and misconceptions, but I feel perhaps there is no other papers on this, but integrated knowledge would be better.
We try to make things interesting by just focusing them on phenomena like the following, that are directly to the point of what's going to be taught afterwards and what makes them understand the limits of what they actually know. So we try not to overload these lessons with too many topics from other areas. We try just to focus on what is relevant and what kind of puzzle we can present them as an entry that makes them recognize there is some interesting phenomenon. Anyhow, I'm not in the position to predict it correctly, nor am I able to explain my prediction, and therefore I feel the need that I would like to get more knowledge about this thing. I say Swiss teachers prefer that because it's more focused and leads directly to the points that they're going to introduce. And
somehow I agree with you, especially when you're teaching preschool and primary, because I think in those ages, well, it's not so important for the students to divide knowledge in the three sciences, but to get their first concepts. So I think it's nice to consider that perspective. Do you use any thinking routines in order to transfer those concepts and to transfer those processes of science from one side to another, or to the life to?
I mean, thank you. One reason how we want to make it more interesting is, for instance, that we have some kind of teaching unit on batteries, so that we refer to some kind of everyday context that makes them aware, well, I'm always using batteries and accus and fuel cells and things like that, and I don't have any knowledge about how they work. So one of our teaching units really has the topic of mobile sources of energy, and this battery topic is embedded in this. And on the other hand, the second question was about
Thinking routines to establish thinking patterns to transfer from one.
Oh yes, of course. I mean, for instance, these inventing with contrasting cases, the intention to improve their transfer achievements, because usually when you just present a theory to students, they tend to focus on surface features. They tend to focus on rules, how to calculate something, but they do not have this awareness of the underlying problem that made people to invent, for instance, this kind of index that describes the slope of linear graphs. And it turned out that even those students who were not able to present the correct suggestion and the correct measure, they had some kind of productive failure, and then even showed better achievements in the transfer tests than those who were just getting the information and then maybe focusing on just surface features. That's how we try to improve that.
Last question. If I understand correctly, in the beginning you show daily life examples, and from the examples you are following the process that you explained. Do you gauge the emotional level of the students when you are presenting this material, or when the students are looking at the experiment or looking at the daily life phenomena that you are presenting? What is your state, whether or not you actually gauge the emotional state of the students when you are presenting this whole thing?
Could you explain this a little bit more about this emotional state? I mean, we try to attract their attention by presenting these stimulating phenomena.
Yeah. For example, when this phenomena is presented to the students, not all the students are curious enough, or not all the students are emotionally in a state where the dopamine is just flowing, so they can receive the information. And some students are in the same state that you are explaining, but other students may not be in that emotional pleasure state or curiosity state. And what would you do to have them engaged or excited about the discussions? I guess he has something.
Are you maybe talking about engagement? Getting engagement from the students?
Somewhat similar, yes. That is correct.
I don't know. We try to get most of them by presenting examples in that way. And of course, if it does not work sufficiently, we can try harder to adopt it better to the situations. But the main idea is to get them by this kind of cognitive activation that they are eager to present some solution to that. And usually it works. Usually 80–90% of the class really participates and gets involved in making hypotheses and develops some kind of justifications why they expect that this bowl will be first and the other will be later. Yeah. Shall we now start with the second presentation?